Let's work on one more example where we're looking for a volume of the solid obtained by rotation of the region bounded by curves. What curves we're talking here about? Y equals 1 over x cubed, y equals 0, x equals 4, x equals 5, and the rotation is happening about y equals minus 1. This means that we're rotating not about y-axis or x-axis, but about another line, y equals minus 1. This line is parallel to x-axis or y-axis. Well, think about it. It's y equals minus 1, so it's a horizontal line. Horizontal is parallel to x-axis. Thus, if we're gonna use, if we're going to use disk or washer method, this is going to be case 1, dx case. If we're going to use shell method, this is going to be case 2, dy case. So that's an interesting thing to remember, or basically helps you to understand what is going on. You can always forget about this and actually understand which case we're using based on the slides. Let's sketch the graph. Step 1, sketch the 2D graph. Well, y equals 1 over x cubed looks like something like this. It's going to be something like this. Okay, now y equals 0, that's x-axis. So that's basically the floor, x-axis. X equals 4 and x equals 5, creating a cut. X equals 4, x equals 5, finally enclosing the area we need to revolve. And the rotation happens about y equals minus 1. So let's draw it. Y equals minus 1 looks like this. So let's decide on the case before drawing 3D picture. Since we are talking about x from 1 to 5, and since y equals f of x, we kind of don't want to solve for x, and you will have to solve for x if you're using dy case. That is why it kind of makes sense to use dx case, since everything is set up for dx. Since we're going to use disk or washer method, we need to decide in a second. Let's draw a 3D picture. I do not recommend drawing a 3D picture for the shell method to avoid the mistake. So I'm gonna copy, not the copy, but 1, 2, 3, 4. 1, 2, 3, 4. I will use y equals minus 4 as the mirror to recreate this shape. You don't have to be precise, but here it is. And now draw several circles to help your imagination to see the 3D object. Here it is. Here is the rotation. Do you see it? Maybe this will help. So now tell me if it's hollow inside or solid. Seems like it's hollow. Because of the shift, you can see there is an empty part inside. So we should take this into account. Since it has an empty part inside, we're gonna use washers. If you don't understand any of this or you don't want to memorize it, then make a sample slice. That's how we teach it. When you create a sample slice, the sample disk will be like this. It will have an empty piece inside, but then something outside. So it's gonna be a ring or a washer, right? Ring. That's how, first of all, you know it's a washer method, because it has some gap inside. And then in terms of dx or dy, you need to tell me how would I know the thickness of this sample disk. Is it going to be located on the x-axis or y-axis? The thickness is this. You see, it's projected into the x-axis. So that's how you know it's going to be dx case. Because the dy basically gives you the height of that ring. So now we know the case, now we know the method we're going to use. We can start building the integral. V is going to be integral from a to b, which is very convenient because we already know a and b. It's going to be from 4 to 5. I can even write it down. from 4 to 5. This is how you know where your 3D picture starts and ends. It starts from this wall, which is x equals 4, and ends with this wall, which is x equals 5. Very convenient. Now I will have pi r squared minus pi r squared. Pi capital R of x squared minus pi small r of x squared dx. Do you remember the meaning of these two areas? So those two areas. Capital radius gives you the solid part of the 3D object. Small radius gives you the empty part. Pi r squared gives you the area of the disk. Dx gives you the width. Remember that? Nice. So multiplying area by the width. Now we need to build both cases, pi r squared and pi r squared. I'm factoring out pi. That just makes sense to do. And then I will first try to create the volume, the radius for the solid object. So kind of ignoring that this object has a hollow piece inside. I will have to see or think how the area of this sample disk will look, how the radius for the area of the sample disk, or in this case ring, will look like if I ignore the empty piece inside. Go to the axis of rotation, here it is, shoot the radius up and see what it hits at the very end. This is your radius. This is the difference between two curves, the area between two curves. Here it is. We know how to find area between two curves. The top function minus the bottom if it's dx case. So, well, it's always bigger minus smaller. The top function is the red curve, which is 1 over x cubed. The bottom function is y equals minus 1. So it's going to be minus 1. Enclose the parentheses and square. That's your capital R. Minus. Now I need to only find the radius of the empty piece. The radius of the empty piece is, find the axis of rotation. Here it is. Shoot the radius and hit the end of the empty part. This is the radius. This is the radius of the empty piece. So we're again looking for the area between those two curves. Those two curves are x equals 0. Well, no, it's actually x-axis, right? So it's y equals 0 and y equals minus 1. So it's going to be 0 minus negative 1. And that's how the shift is being presented mathematically. This minus 1 everywhere represents the shift that we are rotating not about x-axis, but about something which is 1 unit below x-axis. To shift the whole object up, we subtracting that piece, minus 1. It just makes sense. Dx at the end. Now, we just need to finish, simplify everything and finish integration. Pi from 5 to 4, square of sum, because minus minus gives you plus, is going to be 1 over x to the 6 plus 2 over x cubed plus 1, because it's 1 over x cubed plus 1 over there. Then it's going to be minus, it's going to be just 1, so it's not very important. Is it minus or plus? But minus 1. So make sure you understand. This is 1, but there is a minus in the formula. Big radius minus small radius. Nice. Dx. Start integrating from 4 to 5. X to the minus 6 gives you x to the minus 5. Oh, integration happens right now. Over minus 5 plus 2. X to the minus 3 will be x to the minus 2 over minus 2 plus x, because integral of 1 is x. A bar. Oh, actually very interesting. I just realized that this one and this one cancel out. That's why I'm thinking x minus x. That sounds weird. Yeah, they cancel out. From 4 to 5, plug the top minus the bottom. you will have pi outside. It's going to be 5 to the minus 5 over minus 5 plus 2 cancels out with 2, so it's actually minus 5 to the minus 2, put parentheses, minus 4 to the minus 5 over minus 5 minus 4 to the minus 2. Either you keep it as it is, or if you want to know what the volumes look like, then you can approximate it as pi times 0.0226313 units cubed. Or if you really want to know what kind of volume is that, the volume is surprisingly super small, 0.071098 units cubed. We don't know what units are. If units are huge, like kilometers, hundreds of kilometers, then maybe this is not a very small volume. And that is the answer for the problem with using a Washer method dx case, but with a shift. And the shift looked here like so. Don't forget to be careful with negative signs. Minus 1. So that's basically plus 1 if you think about it. Because we want to move it back by 1 unit to match with the x-axis rotation. That's what we're doing. We're adding 1 back, as you can see. So that's a pretty cool idea here. Thank you for watching and see you next time.